All right, I'm going to get started. Well, thank you for the people who came. This is the 6th lecture. Today we're going to talk about semi-definite programming. One thing that I want to mention before I start, the MIT course evaluations just went out. They are due January 28th is the last day you can fill them out. If you have good things to say, please fill those out because they're important both for feedback for me and because, well, essentially because it's important for me to get feedback. I'll also likely be sending out a separate form with more specific questions, just because I know that the feedback form that they give is a little bit more generic. And I'd really appreciate responses so that I can improve this next year and for subsequent years and et cetera. Okay, so today we're going to talk about a subject that's been coming up. I think Benoit brought it up a couple of times. Today we're formally going to introduce the notion of semi-definite programming. Abbreviated SDP. So, before we launch into it, like I said, my philosophy on this course was try to give people some intuition as to why certain things work and why they don't. And again, I'm not going to have any proofs. So first, semi-definite programming is kind of a generalization of linear programming in a very particular way. And so the big jump is from kind of thinking about vectors to thinking about matrices. But matrices are extremely complicated. So we actually do need to restrict. So first we're going to talk about the set of symmetric matrices. So this set, I'm going to denote S sub n. At some point, there will be pluses and minuses. I might flip the pluses and the n from superscript to subscript, just because people use different conventions. But I'm going to try to stay consistent. Okay, so I remember the first time I looked at these kinds of things, I was like, well, symmetric matrices, that sounds extremely restrictive. So why do we even begin talking about them in the first place? This set actually has some pretty nice properties. So for starters, Sn is closed under, so the operation of addition and subtraction, under the inversion operator, and under scaling. So already from property 1 and property 3, we see that it's likely that we're going to be able to do our two favorite things in optimization is take convex and conic combinations. So this is, if you look at different subset of matrices, some of these properties might not hold. Inversion also turns out to be pretty useful in this set, but that's a different story. Another property that they have is that symmetric matrices are what are called normal. So A is normal if A transpose is equal to A transpose A. That seems like a kind of wild and really uninteresting property. But it actually turns out to be extremely important because if a matrix is normal, then A has a unitary eigenvalue decomposition. I'm going to put the star here. Meaning that UU transpose is the identity. So I can do an orthonormal eigenvalue decomposition, and when I say eigenvalue decomposition, I truly mean an eigenvalue decomposition. This lambda is a diagonal matrix. So it's stronger than saying I can perform the Bloch-Jordan decomposition. So that's a nice property. Also, in symmetric matrices, you can define a notion of the inner product of two symmetric matrices. So this inner product, if you've taken any linear algebra or anything, you know that it's really natural to think about inner products, and it's always nice when you can define one in a consistent manner on this, on any given set. And so this is the inner product that is most often used when it comes to symmetric matrices. So there are a bunch of reasons why this works, but these are some of the properties that turn out to be extremely nice in symmetric matrices. If we restrict even further, we're going to talk about a positive semi-definite matrix. Yes, because since they're symmetric, I don't have to take the transpose. You can actually define this inner product between matrices more generally, and typically you take the transpose. But this is just being pedantic, that x and y are supposed to be symmetric. So now, if we look at an even more restricted class of matrices, called the PSD cone, which I'm going to denote SN plus. And so A is going to be in this cone, and we'll talk about why it's a cone in a second, if any of the following holds. So condition 1 is that x transpose AX is more than or equal to 0 for all x. 2. So all three of these conditions are equivalent. And what it's essentially, a matrix A is going to be positive. It's going to, you can think about this as a form of matrix positivity. If it defines a positive quadratic form, and by positive quadratic form, it means that when I take a very nice property when we think about scalar squares is that they're always positive. Matrix squares are the same way. A matrix is positive semi-definite if any of these conditions hold, and they're all equivalent. You can check any of these. And this, for reference, is usually called a Cholesky decomposition. Any questions so far? The cone part is coming. So A is in the set of positive semi-definite matrices if any of these conditions hold, and they're all equivalent. So if you prove one of these about a matrix, you've proven the other two. Okay, so the cone part has not been introduced yet. Cone part, so we're going to talk about why this set is actually a cone in a second. And yeah, go ahead. Good call. The question was about an attendance sheet. If you have a pencil or pen, if someone could make it, that'd be great. Okay, so, and by the way, so the semi-definite part about it, there are also positive definite matrices, and essentially what it means is you replace the first two conditions, you replace them with strict inequalities. And a lot of software will actually require you, if you perform a Cholesky decomposition, to have strict positivity because there are some subtleties about how you do that decomposition. And there are a handful of other ways you can check positive semi-definiteness that I'm not going to get into, but if you study this, you're going to want to look a little bit more into that. So the question about the cone. So why does this form a cone? Yeah, that's essentially what it boils down to. So if x and y are both in Sn plus, then if I take x transpose lambda x plus lambda 1x plus lambda 2y x, well, when I factor this, x plus x transpose this is positive, this is positive, this is positive, this is positive, and so this whole thing is positive. This set also turns out to be closed and convex. I mean, that's not too hard to see. And so the nice thing about cones is that you can use basically cones to define orders. And so this order, in the same way, so if I had a vector that I know is component-wise more than 0, I can say that x is more than or equal to y component-wise if x minus y is more than or equal to 0. So in the same way, the matrix X in Sn plus, so X and Y, we have that X is more than, I'm going to try to be consistent with this curly inequality, but it's kind of hard to draw sometimes. So this defines a partial order because if you take two matrices, if I take the matrix 1, 0, 0.5, and I take the matrix 2, 0, 0, 0.25, if I subtract one from the other, I'm going to get a negative eigenvalue either way, right? So not every matrix can be compared to every other matrix, but there are some matrices. So for example, if I do 3 and 4 here, this matrix is strictly larger because if I subtract them, these are diagonal, so I know exactly what their eigenvalues are going to be, and and those eigenvalues are going to be positive. Go ahead. If I put a 1 in which corner? If I replace this right here? So if you subtract these two matrices, you would get, so the question is, if I put a 1 up here, would this matrix still be considered larger than this one? If I subtract these, I'm going to get 1, 1, 3.75. So the answer is actually yes, because the eigenvalues are still positive. So it has to do with the eigenvalue decomposition here. And I'm appealing to property 2 up here, that the eigenvalues all have to be positive. So like if I have a generically dense matrix and subtract another generically dense matrix, the answer is I'm going to have to do the eigenvalue decomposition to figure out whether one's bigger than the other. Oh, good point. You do need to be symmetric to even talk about these. So importantly, this inequality is only defined for x and y in the symmetric matrices. So yeah, I wasn't paying attention. So I'd have to do, if I put a 1 here and a 1 here, then now I have to do the eigenvalue decomposition because I don't know offhand what the eigenvalues of that are. Okay, so the other unlike my previous lectures, this one I'm going to reserve the examples for the end and talk about the kind of this mathy stuff in standard form at the beginning. The reason for that is people are coming from very mixed backgrounds and may not have seen these matrix properties or these random facts, and I need to use some of them in a lot of the examples. Also, Benoit has kind of given everyone a taste of why semi-definite programming is nice. So the last property for checking semi-definiteness that I'm going to talk about, this is called the short complement. And the reason I bring this up is because this trick is used all the time. So let's say I have a symmetric matrix like this. And I want to check whether this is positive semi-definite or not. This condition is actually going to be equivalent to so this is called the short complement. So when you hear people say taking the short complement of a matrix, what they mean is this matrix right here in the bottom. This is the short complement with respect to A, and this is the short complement with respect to C. So if I want to check that a certain block matrix is positive semi-definite, what I can do is I can just check, okay, is the upper block positive definite, and is this odd-looking matrix inversion thing positive semi-definite? In condition 1, why am I guaranteed that I can invert A? Go ahead.
If it's greater than 0, then it's going to be positive definite and it's going to have independent columns.
So the answer was it's greater than 0, so it's positive definite, so it has linearly independent columns. Well, yes, but you're missing something in the middle. The reason that that is true is it's positive definite, so its eigenvalues are all strictly positive. And so that means I can invert the matrix, because that means I don't have a 0 eigenvalue, and so therefore all the rows and columns are linearly independent. Go ahead. Positive semi-definite means it's greater than or equal to. This one?
Like x equals that.
This is a greater than or equal to. This is the positive, x is positive semi-definite if this holds. If both of these hold with strict inequality, you also can get positive definiteness by checking that, but both have to hold with strict inequality. Go ahead.
Is there a transpose sign missing for the second condition?
Chance that there is a sign missing in the second condition.
Transpose sign.
Yes. There is a transpose missing on the second condition. Thank you. Okay, so those are some of the kind of relevant properties that show up. The normality of the matrices is important because it means I can always perform this eigenvalue decomposition, which allows me to do this equivalence. This ability to say whether all of the matrices are, all of the eigenvalues are positive, essentially allows me to define inner products in a nice consistent way. That means I can have a positive semi-definite norm. This Cholesky decomposition will turn out to be very useful in a later example when we talk about sum of squares. And this cone property is essential because one thing that I want you to take away from this class is that convex programming isn't easy, conic programming is easy. Convex programming is easier than other things, but most of the time people are talking about conic programming.
Can you explain the normal thing again? What was the first thing you said? The normal property is important because what?
So the question is, why is the normal property important? So symmetric matrices are always normal, and normal matrices you can always perform an eigenvalue decomposition of. This is not true about all matrices, right? Some matrices you can only get down to a Bloch-Jordan decomposition.
You said that something to do with these properties on the top right?
So the fact that I can perform this eigenvalue decomposition ensures that I can even talk about eigenvalues in a consistent way and not have to worry about thinking. It means I can diagonalize my matrix, which means I can talk about the eigenvalues, not necessarily think too hard about whether they're repeats or not, et cetera.
Oh, it means they're unique.
They're not no, I did not say that the eigenvalues are unique. What I mean by that is if I have two of the same eigenvalues, then their eigenvectors are linearly independent. I don't have to think about the Bloch-Jordan decomposition. Go ahead.
What actually is the complement? Like, is it the set of conditions?
What?
Or
Can you repeat that question?
so what constitutes the complement? Like, is it the set of conditions? Like I guess the way it's written, it makes it seem like there's x and x has a complement, the sure complement.
Yes. So when people talk about the Schur complement of the matrix X, they're usually talking about this matrix down here. Yeah. And so being very pedantic, the Schur complement, you should be specific about whether it's with respect to A or C, but usually people talk about the Schur complement with respect to A, just because it's natural to think about. And just to be clear, this block decomposition is something that you get to pick. So if I have a matrix here, and I have no idea whether this matrix is positive definite or not, I just put in some numbers. If I want to check whether this is positive definite using this block decomposition, I can pick to divide and have the 2 be by itself, and then I'd be doing the inverse of 2. I'd be doing, this matrix minus 1/2, and then the outer product of these. Or I can also pick to do it. That was the same one. Nope. Also pick to do this one. So you get to pick the block partitioning that you want to work with. And it's true for any block partitioning.
So is there some way to figure out what's easiest?
So the question is, if you're going to use this, is there a right one to pick ever? The answer is that you'll see it come up. If you use this trick, you'll see a natural block partitioning, essentially. Okay, so let's get on. Now that we've talked about semi-definite matrices and its cone. Also, the term negative definite matrix might come up. All a negative semi-definite or definite matrix is the, if you multiply it by -1, it becomes positive semi-definite. That set is not as nice because adding two positive semi-definite matrices makes them positive. But like, yeah, people usually just talk about the positive side of things. Okay, so SDP, the standard form. We'll do this. So the standard form of semi-definite matrix of a semi-definite program assumes it's supposed to be extremely suggestive of linear programming. So in linear programming, the standard form is something like this. And so you should see the parallels immediately. I'm going to be minimizing a linear function, which remember that this is equal to trace C transpose X. So I'm going to be minimizing a linear function of my decision variable, X. In this case, X is a whole matrix. This case, X is just a vector. And I'm going to take that minimization. I'm going to have some equality constraints, and so I'm going to be working on an affine subspace over some cone. So X has to live in the cone of positive semi-definite matrices. In this case, X has to live in the cone that is the positive orthant. And this is just to be sure that I'm doing things correctly and that so AI and C have to be symmetric matrices. Again, this looks very restrictive. This is just the standard form. Your parser can accept much more general kind of statements. And so this suggestiveness is not just, I would say, it's not just artificial, right? It's not just good notation that makes things useful. You actually get this kind of containment of different types of conic programs. Every LP can be written as a QP, which can be written as an SOCP, and every SOCP can be written as an SDP. So this is actually strictly more general then SDP is actually strictly more general than everything else. And so that kind of complexity does come with some other caveats. The reason linear programming works so well is because we've studied it very well, and you can say a lot more things when everything is strictly linear. Once you get to SDP, you'll see how complicated the things that we can express in this language actually are. And it's not surprising that if you want a general purpose solver that can solve every SDP, it has to be much weaker in some ways.
Is there any set strictly greater than SDP that's still within cognitive programming?
Can you repeat that question?
Is there any like set of problems greater than SDP which is still like within cognitive programming?
So the question is, can you define an even larger class that contains SDP but is still a cone program? I haven't studied that question in particular. You can, as long as you can find a cone that contains SDP, then it's definitely possible. A lot of the operations that we do just use the conic structure of the set that we're working on. And so I don't want to say, no, it's not possible, but it's not common, and I haven't really encountered it. So we talked about the standard form. And since we're in the world of convex optimization, it's extremely important that we talk about the dual. So let's take the dual of this convex program. So I treat the dual a little bit differently than Benoit, but essentially, let's start by figuring out what the Lagrangian function is of this program. So we're going to write our objective. We're going to write our linear equality constraints. And this is the cone containment. This is a linear function. This is a linear function. This is also a linear function. So what I'm going to do is I'm going to write this as, okay, so we've got the sum lambda I bi plus c it should be a minus. This is just a Lagrange multiplier that lies in the cone. So it's a Lagrange multiplier. Lambda is PSD. So the question was, what is this capital lambda that I'm writing? So remember that when you take the dual, you have on your inequality constraints, your dual variables should be more than or equal to 0, right? But that positivity or that non-negativity, when you take duals, it should be with respect to the cone that you're in. And so when I introduce a Lagrange multiplier variable on this x that's positive semi-definite, I need to introduce a positive Lagrange multiplier, but with respect to the ordering with respect to the cone I'm in, which is the positive semi-definite cone. actually going to do this. I get to change that sign for free. Yeah, so that. Because it's an equality constraint, I can change the sign of the Lagrange multiplier and it doesn't matter. It's just going to make things cleaner when I write them out. Okay, so the first thing I do is I want to minimize the Lagrangian with respect to x, right? And so in order to do that, I'm going to take the gradient with respect to x with my Lagrangian. And the only place it shows up is here. If you do this derivative by hand and actually work through it, you're going to get I actually don't even need to take a gradient here because I want the unrestricted minimization to be negative, to be finite, right? So already, even without taking this gradient, I know that this matrix has to be 0. Otherwise, when I do the unrestricted minimization, I'm going to get something, I'm just going to go to negative infinity, right? But regardless, I get this condition. And so since I know that this is going to be 0, I then get immediately so what's the objective of my dual? Of my dual function? No, but what I'm saying is, okay, so I took the Lagrangian, so now I'm going to have a function that's strictly a function of the multipliers, right? But I need to take a maximization, so I know that I'm going to be writing max. What's left in the objective after I make sure that the first step, the minimization, is finite? Okay, hold up. I need to be sure that the mic is still capturing. Hello, hello. Yeah, it's still capturing. I don't know what that beeping was. Okay, so in order to have a finite minimum, I said that this linear function that I'm applying to x is 0. So what's left in my objective? Yep. So this is, and I'm just going to write that as lambda transpose b. And then what are the constraints? Right? What are the conditions under which I'm doing this? Right? I get that C plus lambda I AI has to be equal to some positive semi-definite matrix. I don't actually need to carry this equality around. I can just ask for this matrix to be positive semi-definite. Okay, does this constraint right here even make sense?
No.
So the answer, someone said no. Why do you think it doesn't?
It seems that, oh, never mind.
Right, so the red flag that should be going off is I'm asking for a matrix to be positive semi-definite. And before I can even do that, I need to be sure that I'm asking that this is symmetric to begin with. And in this case, it is, so it's OK. That's why it's important that you have these symmetry assumptions on the C's and the A's in the standard form, because otherwise, I mean, things don't really make sense. This version of the semi-definite program is also called the LMI formulation. So this is linear matrix inequality, and it gets that name because this is a linear combination of matrices with an inequality. If you look up the section in Boyd on semi-definite programming, this is the standard form that he assumes. But you see that the dual of it is the standard form, what I'm calling the standard form. So different people have different convention. So I'm going to make a point, and if I have time to go over it at the end and with an example, I'll come back to it. But are these two things equivalent? Is the dual equivalent to the primal? So this is a convex optimization course. So is there a duality gap? Someone is nodding their head, and they are actually correct. So, so for linear programming, there's never a duality gap. And so that's very nice. When it comes to more generally convex programming, there are situations where you can have duality gaps. And so you do have to be careful. Usually, they don't have a duality gap. What you need typically is something called Slater's condition. This is also sometimes called constraint qualification. Sorry for the small writing at the end there. So these two formulations are equivalent for like 99.9% of problems, because all you need is primal and dual must have a strictly feasible solution, strictly feasible point. So what you need for this to be true, for the primal and the dual to have no duality gap, is that you need to have a strictly feasible point. So that means that there needs to be some lambda such that this inequality is strict. This is a positive definite matrix. And you need a positive definite matrix that satisfies this equality. If that's true, the primal and dual will be the same.
What was the one on this side?
You need an X that's strictly positive definite that satisfies the equality constraints.
Sometimes if that condition isn't met, that the primal or the dual, one or the other might have a solution if the other one doesn't.
So the question is, if that condition isn't met, is it true that the primal and the dual might have a solution while the other doesn't? Usually what happens is that they both have a solution that is strictly feasible, but the value of their optimal values are different. And so essentially when that happens, it's because both solution sets are more or less a point that aren't the same point, is the intuition.
Does this also tell us something about how to recover like the solutions? from, is like, this hidden variable here is what, x, and then it's lambda here. If we just solve one of those problems, can we recover the,
So the question is, if you solve one of these problems, can you recover the solution of the other? Yes, you can, right? But usually what you do when you solve these, Benoit was saying, you solve them at the same time because it gives you an idea of what the central path is. But you can solve either one and it's fine. Okay, so the picture I like to have in mind when I'm thinking about semi-definite programming, and this is a useful picture to have for what I happen to use semi-definite programming for the most, which is dynamics. It's not the only way to think about it, but you're essentially allowing yourself to look for a quadratic function. And that doesn't sound like it's much, but it's actually very, very cool. Which board am I on? Let's leave this one. So the examples I'm going to talk about today come from dynamics and stabilizing systems. So the first example I'm going to talk about is an example from control. So we're going to talk about, so let's say I have a dynamic system. I'm going to make it discrete time. So I have some dynamic system that I want to control. And when you talk about control, I'm talking about trying to steer the system to a specific point. In this case, I'll always talk about I'm trying to steer the system to the origin, because that means that I can track something well, or I can achieve a position that I want. And so what I want to talk about in this case is the state feedback problem. I want to design some matrix K that if you give me the state, I know a control action to do. So for example, if you're not familiar with dynamics, if I'm trying to follow a straight road and my state is my angle relative to the road, so if I'm trying to go straight and I feel myself turn to the left, that means I need to apply a certain steering angle to turn back to the right. And the farther I am to the left, probably the stronger I'm going to want to steer to the right. But I don't want to oversteer, because if I oversteer, I'm going to go crazy. So there's a nice fact about linear systems. So if I do this, if I apply this, this controller here, I'm going to that xk plus 1 is equal to a plus bk xk. And I want to be able to find this k such that the system is stable. So what stability means for a linear system is that I want strictly less than 1, right? Because the reason for that is, well, at time xk plus 1, if these are my dynamics, then my state at time k plus 1, I'm just going to be raising this to powers over and over again, which means that this is going to be going steadily to 0. So no matter where I start, eventually I get to 0. So I promised you an example in semi-definite programming. So there's actually an equivalent condition. So there has to exist a P more than or equal to 0, so positive semi-definite P, such that A transpose PA minus P is negative definite. Sorry, this is strict. So, are people willing to just accept that, or do you want me to prove it? It's not too hard to prove. Go ahead.
I have sort of a side question. In differential equations, we saw that systems are stable if the eigenvalues have real components less than 0. Why would we use that sort of definition instead of the other one?
Wait. This is, so the real component being less than 0 is for continuous time systems.
Okay.
This is discrete time.
Okay.
So the question was, in differential equations, usually you think about the operators having eigenvalues with the real part less than 0. For continuous time systems, that's the condition. For discrete time systems, it's actually that you want the modulus of the eigenvalues to be less than 1. In continuous time, there are also LMI formulations of these. I'm just doing the discrete time because the side I picked. The expressions end up being pretty similar.
Can you explain the key thing that you said, the second property? You said you were gonna.
Do you want me to prove why that's true?
Yeah.
Okay, so someone wants me to prove why that's true. So 2 implies 1 because if I take an eigenvector of I'm going to call this A capital K. A capital K, capital K, capital K. Sorry. I made a mistake in my notes. What you need is not that. I need A plus BK, which I'm calling A capital K now, to satisfy this property, not the A. If the A satisfied that property, the A would already be stable. So if I take an eigenvalue, if I take an eigenvector of the A capital K, then I have that strict V transpose A K transpose P A K minus P V. This is equal to lambda squared. So 2 implies 1 because if I take this product here, right, then this is just going to be lambda squared V transpose PV minus V transpose PV. Just from the definition of an eigenvector. And then 1 implies 2, so So the two conditions are equivalent. I'll give you a little bit of time to parse that, but essentially what you're doing is you construct a positive semi-definite matrix based off of this infinite sum, which is guaranteed to converge because of the eigenvalues of AK. And so there's kind of like an arbitrary choice you can make of this is one that satisfies that condition. Okay, so I want to find a K and I want to find a P that makes this stable. So let us write down find PK such that A plus BK transpose P A plus BK minus P strictly less than 0. P is strictly more than 0. Okay, so strict inequalities are typically bad in semi-definite. I mean, you always want to have closed sets. So, but the way you typically handle strict inequalities is to just put a small epsilon and make it more than or equal to, and another one more than or equal to. But I don't want to carry that around, so we'll just assume I can leave the strict ones in there. Okay, so this is really not nice, right? And of course I erased it, but do you guys recognize something I mentioned at the beginning of the class? It's the last of the things I talked about with symmetric matrices. Sure complement, yes. So let's write this down as a sure complement. So this condition is equivalent to P A plus BK transpose P A plus BK. I need to put the P here. And then another P. Does anyone see an impending problem right now with my decision variables? So my decision variables are P and K. And in here, I'm going to create something like PA, okay, that's fine, plus PBK. What am I doing to my two decision variables? I'm multiplying them, yes. So this is bilinear, so it's not convex, which is kind of a bummer. Luckily, this is one of those problems where if you choose not to give up, you can actually do something somewhat magical. It's a lot like the graph programming problem example I did it right at the beginning is, okay, I got to a formulation, and I'm going to try to do something more and see what happens. So let's take that, let's do this example. So if this is positive definite, if I were to So if this is positive definite, this is also positive definite. And if this is positive definite, the converse is also true. Right? So now let's carry through this matrix multiplication. And we're going to get, let's do P inverse A plus BK P inverse. Okay, so now you're going to tell me, okay, I haven't done anything magical. I just, now instead of having a bilinearity with P and K with B sandwiched in the middle, I just have a bilinearity with the inverse and it's all the same. Also, by the way, remember when I said that inversion property is important? If P is a positive definite matrix, its inverse also has to be a positive definite matrix because it's still a symmetric matrix. Its inverse has the eigenvalues that are the reciprocal of the original matrix, and so it has to be positive definite. Also, the attendance code for today is Lyapunov. Talk about that name next. Yeah, that's what I wanted to do. I spent too much time erasing. Okay, so have I fixed my problem? Well, on the surface, it doesn't look like it. What happens if I introduce the variable y is equal to kp inverse? And I'm just going to call q as p inverse so that I'm not carrying around some inversion that looks wrong. So in these new variables, what does this inequality, what does this look like? This looks like qa transpose y transpose b aq plus by q. Are there any more bilinearities? Is this problem exactly equivalent to this problem over here? All I've done is some renaming. Someone said yes. Do you see where there might be some weirdness involved? One thing I forgot to put, if this is my optimization problem, find only subject to these constraints. Is Q related to Y? Yes, they are related. Is it related to Y in a way that's nice and convex? So the guess is yes. The answer is no, because if I do that, I'm going to have to reintroduce K, and that's what I'm trying to get rid of. But the thing that's nice here, and this does not happen with every problem, I can do this. It's technically a relaxation of that, or it looks like one at first. But if you give me a Q and a Y, I can recover the K because Q is invertible. So I've gotten rid of any weird dependencies that might happen, et cetera, et cetera. So now I can look for a quadratic operator, Q, and some other function Y, and some other just linear map Y that actually gives me a controller that stabilizes the system. And I can add all kinds of costs on Q and Y however I want to do it, but this is one of the basic ideas in linear control that lets you find certifiable stability things. So you might tell me, okay, sure, this is a fine thing to do for stabilizing systems, but most systems aren't linear. I'm going to respond most systems are close to linear around most points. But it's kind of fair that, you know, people have been working on these problems for a long time, so it's kind of fair that you want to do something more powerful. So let's talk about polynomial systems. So what this P is acting as is it's a certificate that the system is stable. So if that P exists, there's like a certificate of stability. So we can actually generalize that. So let's say that I have a function. Let's say I have a dynamic system, x dot of, let's do dx dt is equal to f of xt. So if I want to say that this is stable, I have a very, very similar looking notion. I want to find a function Vx of t such that Vx of t is more than 0 for all x and I need dv dt is equal to dv dx is less than 0. Sorry, what?
So you don't need time independence of your dynamics?
Someone just asked, do you need time dependence of your dynamics? My dynamics do depend on time because the x depends on time. I'll drop the inner x's sometimes, but, and then I need. So a function that satisfies these conditions is called a Lyapunov function. And so if you give me a dynamic system and a Lyapunov function, the Lyapunov function serves as a certificate that this function, that these dynamics are stable. So this condition for all x is kind of usually asking a little too much, so we're actually going to talk about this row set of x such that v of x is less than or equal to rho. So you can ask for all x, that'd be global stability, or you can ask for a region around some sublevel set of this Lyapunov function, which basically means if you evaluate a Lyapunov function at a specific time, you can't escape. Because as the dynamics evolve, what this condition is saying is I'm decreasing along the dynamics. So there's a function that's always more than 0, but decreasing, so eventually I have to get to 0. So we want to look for this Lyapunov function. You might ask, how in the world are we going to do that? Okay, so the first thing I need is I need v of x to be more than 0. So I can't search over all possible functions more than 0. There is a class of functions I can look for. So let's say that v of x is equal to the sum of I equals 1 to m and qi squared x, where qi is going to be some polynomial. Okay, so I'm taking some polynomial. When I plug in x to that polynomial, x can generally be multivariable, and I square it, I'm going to get a positive number. So if I can write down something that's a sum of squares, obviously that's positive. So that at least, now I've cut down my class a lot. So now,
Can it be equal to 0 if x is the root of qi?
yes. So the question was, can this function be equal to 0? The answer is yes. Generally, enforcing strict positivity, again, is hard, but you could ask for these guys to be strictly positive if all of the functions involved have no zeros. Okay, so let's think about the function q1, q2, and so on, qn. When I write down a polynomial, so if I write down p of x, I have, some a0 plus some a1 x1 plus some an xn. And if I want to make it quadratic, I could have, 1, 2, 3, x1, x2 squared plus x n to the 5th, dot, 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 right? I can have all kinds of products of x, which I'm going to call the indeterminants in this. But at the end of the day, a polynomial is defined by its coefficients. And notice that the coefficients are entering linearly into the problem. So any polynomial I can actually write as, some A transpose times some basis. Does that idea make sense to people? It's a little, I get it's a little abstract and weird. But the thing I'm searching for, if I'm looking for a polynomial, I'm actually asking a question about its coefficients, and those coefficients are entering linearly. So that means if I want to write down as a vector this polynomial in terms of x, it's just some matrix of coefficients times some monomial basis. And that basis can have, linear, quadratic, whatever terms you want. But this means that v of x is going to be equal to m transpose q transpose m of x transpose q transpose q okay? So what I'm doing is, what I've shown basically is that if I want to write v of x as a sum of squares, really what I need to do is I need to search for a positive semidefinite matrix. There's this equivalence between searching for positive semidefinite matrix and searching for quadratic polynomials. So
Just a vector here,
what, this q or this q?
that cube,
This is a matrix, right? So the first row of q, of the capital Q, is the coefficients of q1. Second row of q is the coefficients of q2.
yeah, but why do you need to do this? Like, why is this more expressive than just having one polynomial? You're doing the sum of squared polynomials, right?
Yeah, so I'm showing how you get from asking for sum of squares to finding one. Because remember, with SDP, I can actually search for matrices where P is going to be positive semidefinite. So to give you an idea, when I say that semidefinite programs, you're asking a lot and it's very complicated, and that's why sometimes they don't scale as well as you'd like. The searching for for sum of squares polynomials is a subclass of that problem. And you can use searches for sum of squares of polynomial to do extremely, extremely complicated things, like global polynomial minimization. Okay, so I've shown that I've shown a way to ask for a positive definite function. For a positive definite function, meaning I can find this. It's a subclass, but at least it's something I can look over. And if I take the derivative of a polynomial, multiply it by another polynomial, I get another polynomial. So if I was looking for all x, if I was looking to satisfy this condition for all x, I'd really be looking for find v of x such that this condition holds and this condition holds, which I just showed you can write down as semi-definite programs, right? If you want to do something stronger, so if you want to, you're asking a lot by saying for all x. So if I want to search only over this set, what I'm really asking for is an implication. So this is a theorem that I'm not going to go over, but this is called the positive Stellensatz or the P-Satz, if you're not German and can't say it. But this, a sufficient condition to imply this is there exists lambda x sus such that sorry, which one?
Lambda x, vx minus something. What is that?
This is the row. Okay, so now, well, I want to find the biggest set which I can certify converges. So now I actually have an optimization problem. Maximize row, subject to, right? So I need that v of x is equal to mx q mx, right? Q1 is PSD. I need to have that lambda x vx minus rho. Yeah, that's fine. Minus dv dx of x.
Rho just a constant or like a scalar over all of an entire domain of V?
Rho is the sublevel set. So for all x's, which are less than or equal to rho, like rho is just some constant that I'm looking for. And I'm trying to certify that as long as you start underneath rho, so, V could have some really weird sublevel sets that contain the origin. Right? This is some rho 1, this is some rho 2. They can be extremely complicated sets. But I want to find a function where I know that if I start inside of rho of that function, I'm going to the origin. What do you mean we gave up on finding the P matrix?
That formulation, like,
So the question is, we gave up on finding some P matrix. No, we haven't given up on finding any P matrix. Sorry, I switched letters. All of these Q's should be P's. So yeah, essentially, now I've written down an optimization problem where I can actually do something, right? Because all of these P's, they're just semi-definite matrices that I'm looking for. So I can search over them and actually try to find something. The problem here, if you pay very close attention, so the decision variables are lambda. So lambda x is uniquely defined by this P2 and vice versa. But notice that lambda x and rho here are two different decision variables that I'm multiplying together. Bilinear, not so great, right? But what dimension is rho? It's one-dimensional. And if I can certify a sublevel set of, say, if rho is equal to 2, if that's good, and I can find a certificate that I'm stable there, what do we think that means about rho is equal to 1? I can also find a certificate, right? So this is what kind of optimization problem?
Wait, where does the second condition come from? Like, that was on the whiteboard.
Where does the second condition, this one?
Yeah.
This is just a theorem. It's called the p-sats. If you have implications of this kind, a sufficient and sometimes necessary condition is the existence of this sum of squares thing.
And wait, why do you have this thing on top? The bx plus
We have that because, so if you want to do this for global non-negativity, so if you want to do this for like global convergence, then, it's great if you can. But if you're trying to certify that you've written a controller for Atlas to balance on one leg, well, it's probably pretty good if it's here and here, it can recover. But if I push the robot and it ends up in some weird angle, it's going to fall, right? So it's not every x in my state space where that controller is going to work. And so I want to know how well it works in a family, in a region of my state space.
So that's where the bx plus equals b comes in.
And that's where the rho comes in, yeah. Because it's saying that if you give me a state space, if you give me a position in state space that I start at, I know that I'll be able to balance. Because if you start there, v of x is going to go along some trajectory that's going to get to 0. And so I'm going to have, v of x is kind of a stand-in for an energy function.
So how does the p? Oh, I guess the p is right.
Are you talking about the rho, or are you talking about the
Like,
p matrices?
I was following it, and there's just like a v of x plus equals p. I just don't understand how that derives and like why it is.
So
Oh, actually, there's some condition on the right.
yeah, so so conditions 1 and 2, if they hold for all x, I have global stability. But if I find some v where it holds for some rho, so if I find a v that behaves in a specific way, in this way, but it only really works for x is less than or equal to rho, then it's also good, right? Because you're not going to get global stability for every system. It's just not possible.
so, what is so like an example of the Atlas thing, like how is the control represented? Which variable is here?
So the question is, where's the controller in this problem? And the answer is, this is what you would do if you wanted to, if you designed a controller and then wanted to check whether when I put it in the loop it's stable. if you want to design a controller that does stabilize using this method, you're not going to be able to do the same trick that we did with the linear system, where you
Even if you have the controller, where like what does the controller represent? Does it represent as a polynomial of a basis set or something?
no. Where the controller's coming in is these are the closed loop dynamics.
Oh, the fx.
The f of x is the closed loop dynamics of my system.
Velocity evolve as a function of the current state. So the f is encapsulating the controller.
So the question is the f encapsulating the controller? Yes, right? Because what I'm doing is, so like in the context of linear systems, I have x is equal to axk plus b uk, right? But as soon as I make a controller, uk is equal to some f of xk, right? Then the closed loop becomes just a function of this variable xk, right? As soon as I make a controller that's a function of my state, the closed loop is only in the variable of that state. All right. For those of you who came in late, there's the course evaluations have gone out. They need to be in by January 28th. I'd really appreciate if you filled that out. I will also be sending out a survey about this course that might be more specific. I'd appreciate that feedback as well, because I'm trying to become a better lecturer and do a better job on this course. So with that, I will be talking about mixed integer programming on Thursday, and the projects are due ostensibly Friday, but if you need a little bit longer, well, that's okay. So thank you for coming.